bisector? A bisector of a segment, okay, so remember bisect means it cuts it in half. Okay. That's also perpendicular, so it cuts the segment in half, but it's at a 90-degree angle. In a triangle, it's perpendicular to the side and it bisects it. Now, we can have two different kinds of bisectors in a triangle. We can have just any kind of a general bisector that comes through, and bisects the side. Or we can have a very specific bisector that comes through and is perpendicular. Okay, so with a perpendicular bisector, you get two situations. Each side of the triangle is, or each side of the bisector is equal, and you have that 90-degree angle. You can even have a bisector that comes from the vertex like this, but it's not perpendicular. So it's not a perpendicular bisector. It has to be perpendicular to be a perpendicular bisector. And as you can see, in some triangles, that won't line up, stay inside the triangle. In other triangles, like if you have, for example, say an isosceles triangle, it might line up inside the vertex. And that states that if a point Okay, so the perpendicular bisector theorem tells you that if a point is on the perpendicular bisector of the segment, so any point on a perpendicular bisector, it will be equidistant from the endpoints of the segment. So if I have a triangle and it has a perpendicular bisector that hits the vertex of the other side like that, not only do we know that these two sides are equally distant because that's the bisecting, because this point here is on the perpendicular bisector, I know that these two sides are also distant, equally distant. So in other words, if I take any line segment and I bisect it perpendicularly, okay, any point on this line will be equally distant. So this distance will be the same as that distance. If I put a point down here, this distance would be the same as this distance. If I put a point up here, this distance will be the same as this distance. Okay, so any point on that line will be the same distance from the ends. Okay. Then we have the converse of the perpendicular bisector theorem, which says if a point is equidistant from the two endpoints, oops, sorry, not if we're going to get a line segment. So if you have a line segment, and and there's a point that's equidistant from the two endpoints, anywhere out in space, then it's on the perpendicular bisector. So now if I have some line, I'll call the endpoints, say A and B, and I have some point out in space C, and it turns out that this distance and this distance are the same, then that means that C happens to be on, well, that's not quite right. Close enough. Happens to be on the perpendicular bisector. So this is one of those theorems that kind of goes both ways. If you have a perpendicular bisector, any point on it is equally distant from the ends. Or if you have a point that's equally distant from the ends, it's on the perpendicular bisector. Theorem to find measures, okay? What you look for, you're going to be looking for this perpendicular indication, this little square right here that tells me it's perpendicular, and you're going to be looking for this because this tells me it's a bisector. Okay? Once I know that this is perpendicular and that it's being bisected, I know it's a perpendicular bisector, and then that tells me that this length and this length are the same. So if AD is 4.1, AB is also going to be 4.1. Okay. Here, this is going kind of the backwards way. I'm looking at the fact that I have this perpendicular and that these two lengths are the same. That tells me that this is a bisector, which means that this length and this length are the same. So if this is 3, then this will also be 3. So that makes WY 3. And then again, I've got my 90-degree angle, and I've got the bisecting, which tells me that this length and this length are the same, and now I have algebra that I have to do, but they're the same, so I set them equal to each other. Oops, minus 7. Okay, and then solve it from there. Subtract 2x, and I get 2x minus 7 is equal to 3. Add 7. 2x is equal to 10. Dividing by 2 tells me that x is equal to 5, but I'm not trying to find x, I'm trying to find RT. Typo. Sorry, I'm not trying to find RT at all. I'm trying to find RS. So to find RS, I know that x is 5, so I plug that in. So I get 20 minus 7, so it's 13. So RS is 13. But I had to find x first. All right, so when we look at this, I've got perpendicular. I've got that these two sides match. So that tells me that these are equal. And so I'm going to solve that by setting those equal to each other. So 2x minus 17 is equal to 1. Add 17 to both sides. 2x is equal to 18. Divide by 2. And x is equal to 9, but I didn't want to find x, I want to find FG. And FG is 5x minus 17. So I'm going to plug in the 9 for the x. So I get 45 minus 17. So that's 28. 28, yeah. All right, what did you get for number 2? Anybody? Oh, I'm sorry, I didn't have that, did it? I should have had that. Did that help? Anybody know what this should be now, this length right here? Nobody? Yes, it'll be the same, so 4.2. Okay, how about TU? Did everybody get this? I didn't put in all the steps because I couldn't see what I was writing, but you subtract 2x from both sides and then add 30 to both sides. You get 3x equals 54, and then 3 goes into 54 18 times. 2 times 18 is 36, and 36 plus 24 is 60. That's this distance right here, TU. All right, then we have this concept of concurrent lines. Okay, concurrent lines occur when 3 or more lines intersect. Okay, so if 2 lines intersect, they're just intersecting lines. Okay, but if you have 3 or more lines that intersect at a common point, these are called concurrent lines. So if I have, 3 lines that come through and that didn't quite work, and they intersect at this same point, these lines are concurrent lines. Okay. The point of concurrency is the point where 3 or more concurrent lines intersect. Okay, so that point right there is the point of concurrency. Okay. Okay, then you have what's called the circumcenter of the triangle. Now, what happens is when you have a triangle, it has 3 sides, correct? Everybody agree? Triangle, 3 sides? We're good on that? Okay. Each side has a perpendicular bisector. Okay, so I'm just going to write that on here. So in a triangle, 3 sides, each with a perpendicular bisector. Now, if I draw those 3 perpendicular bisectors on the triangle, they will be concurrent. Okay, so if you actually take a triangle and you actually find the bisecting point on each side and you actually draw perfect perpendicular lines, they will all meet at the same point. Those lines are concurrent. Now, this doesn't happen with every line in a triangle, but with certain lines in triangles this happens. Okay, so the 3 perpendicular bisectors are concurrent and they meet at what's called the circumcenter. So what you have is this is the point of concurrency. For the perpendicular bisectors of any triangle. Okay. So if I draw a triangle, any triangle, and I bring in perpendicular bisectors, to extend that further. They will meet at some point. Okay, and that point is the circumcenter. Okay, now we're assuming that I actually drew correct perpendicular bisectors and this all worked, okay? Here's another example. Sometimes it occurs inside the triangle. So these are all perpendicular and they're all being bisected. Okay. And the circumcenter theorem is a theory that we get about the circumcenter, and this is a fact. Okay, so the perpendicular bisectors of a triangle intersect at a point called the circumcenter. And that point is equidistant, so equally distant, from each vertex. Okay, so if this is our circumcenter, so if P is a circumcenter, okay, AP is going to be the same distance as BP is going to be the same distance as CP. So if this is actually a circumcenter, this distance, and this distance would all be the same. So from a circumcenter, the points of the triangle will be all the same distance. Okay. Now the circumcenter can be on the interior, exterior, or on the side of a triangle. Okay. If you have an isosceles or an equilateral triangle, equilateral, your circumcenter will be inside the triangle. Okay, if you have a scalene, I could also say acute, or an obtuse triangle, it can fall outside. And then if you have a right triangle, it will fall on the side. Okay, so, and that the reason it falls on the side of a right triangle is because this is always 90 degrees, so when you hit the 90 degrees here, it makes it on the side. Okay. But no matter which case it is, whether it's inside or outside or on the side of the triangle, the distance from the vertex to the circumcenter will be the same. So this distance is the same as this distance, is the same as this distance. Over here, we would actually have to draw lines, but this distance would be the same as this distance would be the same as this distance. Okay. And then on this one, this distance is the same as this distance is the same as this distance. Okay, so they're always, this point is always the same distance from the points of the triangle. We're saying P is the circumcenter. So that point right here, that's P. I don't know why it's so far over. P is the circumcenter. We want to list any segments congruent to the segment that they're listing. Okay, now remember, the circumcenter occurs with perpendicular bisectors. So I'm going to go through and we're just going to label everything that's congruent in here, okay? Each of these lines is a perpendicular bisector, so that means this length is the same as that length. This length is the same as this length. And this length is the same as this length. Okay, because of the bisecting. Then because of the fact that this is the circumcenter, this length, and this length will all be the same. Okay, so you've got two things happening here. You've got bisecting, which gives you equal halves of each side. And then you have that circumcenter, which gives you the equal distance to the points. So BR is right here. So the segment that's the same length as BR is RA. Yeah, you could use, yeah, you can just do that right there. CS is this piece right here. So the thing that's the same length as CS is SA. And then BP is this segment here. So this is coming off of the circumcenter. So it's congruent to two other sides, PA and PC. If we knew for a fact that this was like an equilateral triangle or an isosceles triangle, like if this was isosceles, then these two would also be the same as those two. And if it was equilateral, all 6 of these would be the same because the sides that match are being cut in half, so the halves would also match. Does that make sense? We don't know for a fact that this is not isosceles, but if it were, then that would occur. But you'd have to be told. You know, like triangle ABC is isosceles. And then you could say, okay, well, if they were asking me about this, then I would have 3 things that matched it. Does that make sense? This, what I did here with marking everything that matched first, is a good technique. Okay? Because then once you've gone through and analyzed the picture and you've marked everything that matched, that makes this over here much more simple. Then you don't have to try to go figure it out and look for it. You've already got it done. Next, after we have perpendicular bisectors, we have angle bisectors. And an angle bisector is a ray or line segment that bisects an angle. Okay, so if I have any angle, the angle bisector is going to come in, and that's not a very good one. Let's see if I can adjust it. There we go. And it's going to cut this angle in half. So this side and this side will be equal. Okay. The angle bisector theorem tells us that if a point is on the angle bisector, so what I'll have is I'll have some angle. Okay. And then I'll have an angle bisector, which that's not quite. Okay. So if I have, we'll call this angle ABC. And I'll say this is B. Okay, so if BD is a bisector, and I put some point on that bisector, any point at all, what would you like to call the point? Okay, Q. Just because we haven't used Q in a long time, and I like that letter. And I take this And distance is always perpendicular, so that distance, that's not perpendicular. We'll just say it's perpendicular. This distance here will be the same as this distance here. So I'll just call this QP will be the same length as QR. And it'll be perpendicular to the side of the angle. But anywhere, so if I took another point here, then this length is going to be the same as that length. Or if I take this point out here, this length is going to be the same as that length. So anywhere along that bisector, I'll be the same distance from the sides of the triangle. And it kind of makes sense if you think about it, because the bisector is cutting the angles in half. Well, if you're cutting the angle in half, that would mean like the two kind of wedges on each side are going to be the same size. And so anywhere you go along the wedge, the same width. Does that make sense at all? We also have the converse of the angle bisector theorem, so it's kind of like the converse of the perpendicular. It goes the other direction. So we have, if a point is equidistant, oh actually, let me change, make that, oops. It has to be on the interior of the angle. Is equidistant from the sides. Or of the angle. Okay, so what we had before is if you had an angle and then you had a bisector, then the point was equally distant from the two sides. This way we're going the opposite way. If I have some point here, helps if I switch back to pen. We have some point here, B, and this length is the same as this length, then B is on the bisector. So if I came in and I drew a line here through B, these two angles would be the same. We have angle bisector theorem. Now, this should be marked like that. Okay? On your test, this would be marked like, oh wait, no, I'm sorry, that's not marked. I'm going the wrong way. Okay, these are marked. See how these distances are the same? This tells me, if this distance is the same as that, that tells me that this is an angle bisector. And because this is an angle bisector, that means it's cut in half. So if this is 58, this is 58. Okay. Here, on number 5, the fact that both of these are 19, that tells me it's an angle bisector. So that means that this is equal to this. So I'm going to have to set those equal and solve it. So I get 5 is equal to 5x, so that makes x1. But I don't want to know x, I want to know IU right here. And IU is 7 times x, which is 7 times 1, which is 7. If we have this situation again, these distances are the same, so that tells me that these angles are the same. So I set them equal to each other. Solve the algebra. I know how much you guys love algebra. Okay, but you might like it better than proofs. Okay, and I'm looking for angle MYW. MYW. Now make sure on these that you look for the correct angle. MYW is half. That's okay. So we can just plug x in and find out what it is. But if they ask me for PYW, I'd have to solve for this and then double it. Okay? So make sure that you solve the correct thing. Plug in your x, you get 6 plus 5, so you get 11 degrees. So just like, I'm going to come down here, just like every triangle has 3 perpendicular bisectors, a triangle has 3 sides, which means it has 3 angle bisectors. Okay? And they're concurrent. And the incenter is the point of concurrency for the angle bisectors in the triangle. Oh, okay, so when you have the perpendicular bisectors, you get the circumcenter. When you have the angle bisectors, you get the incenter. I know that the names are too close, and that's another part that makes it kind of hard to keep track of which is which. Okay, the incenter theorem says that the angles of a triangle, the angle bisectors of a triangle, intersect at a point called the incenter. Okay, so with an incenter, okay, we come in and we have these angle bisectors. And I'm going to have to adjust. Okay. That's pretty close. Okay. So what you'll have is you'll have these angle bisectors. Okay. And they'll meet at this point called the incenter. And what happens is the incenter is equally distant from each side. Okay, so when you had the perpendicular bisectors, you're equally distant from each corner. When you have the angle bisectors, you're equally distant from each side. Now, it can look confusing because these are perpendicular also, but they're not bisecting the sides. So this length and this length are not going to be the same. Okay? And same here, this length and this length are not the same. This length and this length are not the same. These are the only lengths that are the same. Kind of looks like a face. going to find all the missing labeled parts of the triangle using the incenter theorem. Okay, so what we're going to say is that this is an incenter. Because this is an incenter, that means that these are angle bisectors. Because these are angle bisectors, those match. Now I don't know these, but that's okay because I've got that this is 64 total, and this is 68 total. And I can do 180 minus 64 and 68. That doesn't work. I made a bad triangle. I gotta fix it. Let's do 22 and 14. Sorry about that. I made an impossible triangle. Okay, so I do 180 minus, this is going to be 44, and this is going to be 28. Okay, so I gotta hurry. Okay, so I do 180 minus 44 and 28, and I'm left with 108. If I divide that by 2, that tells me these two angles, 54 and 54. Now, I did this because we're trying to find this length here, because these lengths are all the same. I have a 12 and a 15, and this is a right triangle. And so what do I know about a right triangle? You guys remember that guy? Pythagorean theorem. So if this is A, and this is B, and this is C, 12 squared plus B squared is equal to 15 squared. So 144 plus B squared is equal to 225. So B squared is going to be 225 minus 144, which is 81. So B is 9. So this is 9, which makes this 9 and that 9, because those lengths will be the same.